Okay, we'll maybe get going. So, welcome back everyone to session 5 of World of Groupcraft. Our next speaker is Gabriel Corrigan from Glasgow, who will be talking about finiteness properties of some automorphism groups of RAAGs. Over to you.
Okay, well, thank you very much for inviting me. This is a really cool sounding event. And yeah, it's a cool thing to be part of. So yeah, I I'm sure that we have not managed to get through 18 hours of geometric group theory without someone defining a RAG. But just in case anyone hasn't been here for all 18 hours, as if I have, I will start with the definition of a RAG. So I'm going to have gamma always being a finite symmetrical graph, so I'm not allowed any single loop, single edge loops and no multi-edges. And the associated right-angled Artin group, or RAAG, is given by the presentation I've written here. So each vertex is a generator, and two generators commute if and only if the corresponding vertices are adjacent in the graph. Okay, so there are sort of two extremes here. I could have gamma with no edges whatsoever, and say it's got n vertices, then this will be precisely the free group of rank n, because there are just no relations at all. Or the other extreme is that I've got every edge I possibly could, in which case gamma is complete, and then I've got the free abelian group of rank n. And RAGs are somehow a class which interpolates between these two extremes. And then you can begin to ask questions like, oh, well, if Fn satisfies this property and Zn satisfies this property, do in fact all RAGs? And there's lots of questions in this direction. Today we're going to be looking at outer automorphism groups of RAGs, and one could say, okay, well, I've got out of Fn, I've got out of Zn, which is GLNZ. In what sense does out of a RAG interpolate between these two in any sort of sensible way? This is a sort of ill-formed question, and you can also just answer it with a no if you like, because, for example, out of Fn and GLNZ are both virtual duality groups, but it has been proved that out of a RAG is not in general. But I'm not going to end the talk with that and just say no. We're going to sort of approach it from the out of Fn side of the spectrum, and we're going to be in particular at the start looking at this thing called the untwisted subgroup U of A gamma, which I'll define now, and I'll explain why I've drawn it slightly over to on the free group side, if you like. So here's a theorem. We needn't actually pay too much attention to it. It was conjectured and partially proved by Servatius in 1989, and then proved by, like, it was completed by Lawrence a few years later. So it says that the automorphism group of a RAG is generated by the following sort of families, and then out is generated by the images under the quotient. So we've got graph symmetries. If I sort of flip my graph, I can permute the vertices, and that's going to give me a perfectly good automorphism. I can invert a generator. I can do something called a partial conjugation. Let me not define it. And then there's folds and twists, which are sort of, they have the same form, but twists in particular happen when two vertices commute. Okay, and you might have already guessed that the untwisted subgroup is precisely the thing where we throw out all the twists. Okay, so it's going to be generated by the first four of these families. And given that twists can only happen when two vertices commute, then sort of the untwisted subgroup is kind of more like it's more on the free group end of the out of RAG spectrum, if you like. You cannot have twists in a free group, or out of a free group, because no vertices commute. Okay, so we will. We're going to be working from something that exists for free groups, and it turned out to be easier to sort of go via the untwisted subgroup first, and that's where we're going to stop off. So here is the thing for free groups. So this is that was sort of is the starting point for the rest of the talk. So Mark Culler and Culler-Vogtmann in 1986 built this complex CVN. I mean, okay, they didn't call it CVN, but we do now. We also call it outer space. And the point is that this is, okay, it's not quite a simplicial complex, but it basically is. But the key point is it's a contractible complex upon which out of Fn acts properly. Okay, so with finite stabilizers is what we're going to say. And actually, even better than that, there's a deformation retraction, which is equivariant with respect to the out of Fn action. down to this thing called the spine, and I'm denoting this Kn. So obviously Kn is also contractible, and sort of even better, the action is not only proper, but now it's also co-compact. So the quotient by the action is compact. Okay, and this is good news for reasons that will come clear shortly. I've taken advantage of the fact we're using technology. I've included a little picture. This is sort of CV2, the outer space for the free group on two generators. I don't have time to start explaining where this picture comes from or how you make it or anything, but Culler-Vogtmann has 3 surveys on different aspects of this. So I highly recommend, and I've lifted this from one of those. So I highly recommend going to check those out if you want to learn more. Okay, so the application that we're going to be concentrating on, to start with anyway, is to compute the virtual cohomological dimension of out of Fn. Okay, so this VCD. So let me quickly define that. So I'm going to so for any discrete group, G, the cohomological dimension is the supremum of all of those ranks of non-vanishing cohomology groups for some ZG module M. Okay, in other words, it's the minimal length of a projective resolution of G of ZG. Okay, I'm just going to be working over Z. One can do so a bit more generally, but we're not going to. So you'll notice that if G has torsion, then all of the even rank cohomology groups are going to be non-vanishing, so this soup is infinite or undefined or something. And our groups do have torsion, you know, like inversions, for example, are not infinite order. But we're saved by the following theorem. So the earliest attribution I can find for this is for Serre. This is in Brown's cohomology of groups. So if I've got 2 torsion-free finite index subgroups of my group G, then and their cohomological dimensions are finite, then in fact they're equal. Okay, so this means if I've got a virtually torsion-free group G, then there is a well-defined notion of its virtual cohomological dimension, and I just declare it to be the cohomological dimension of any of these torsion-free finite index subgroups. Okay, it will happen that all of the groups that I'm taking the VCD of are sort of clearly of this form. Okay, so if that was a little bit of, or a lot of algebra, then let's just say this is a natural sort of algebraic notion of dimension, which we're going to be interested in comparing to the algebra and geometry that we know about the groups from other perspectives. Okay, and the sort of key proposition that's really going to make everything go is that if I've got a virtually torsion-free group G like this, and it's acting again with these adjectives, proper and co-compact, on a particularly nice complex. Let's not worry exactly what a proper GCW complex is, but everything again will be. But crucially, the absolutely crucial condition here, aside from being a proper and co-compact action, is that X is contractible. Then the VCD of G is bounded above by the dimension of this space X. Okay, so if I manage to find a complex upon which my group is acting particularly nicely and the complex is contractible, then I've got an upper bound on my VCD of my group. Okay, so we've managed, this already is matching this notion of dimension for the group to sort of a more like normal geometric notion of dimension. Okay, so we can sort of apply this straight away to get the following corollary, and this happens in the original Culler-Vogtmann paper. You can compute the VCD of out of Fn to be exactly 2n minus 3. Okay, so we're going to do this by getting an upper and lower bound that coincide. The upper bound, we've basically just said how we do it. I'll scroll back up to the theorem. I've got out of Fn acting properly and co-compactly on Kn, the spine, which is contractible. All the other conditions are satisfied, so the VCD of out of Fn is bounded above by the dimension of the spine, which it's not so hard to compute, is 2n minus 3. Okay. On the other hand, you can chase through the definitions to show that if I'm a group G and I've got a subgroup that's free abelian of rank K, then my VCD is at least K. Okay, so we can find a free abelian subgroup of rank 2n minus 3 in out of Fn, which means that the VCD of out of Fn is bounded below by 2n minus 3. Okay, so just sort of straight off the bat, there we go. The VCD is 2n minus 3. And this was really easy given the big theorem of Culler and Vogtmann, given outer space. Okay, so let's try and do this for RAAGs in some sense. And the first step here is a paper from 2017, where Ruth Charney, Nathaniel Stambach, and Karen Vogtmann produced what we'll call an untwisted outer space. Once again, this is a complex upon which the untwisted subgroup is acting properly. Once again, it's contractible. And once again, there's an equivariant deformation retract down to the untwisted spine, now K gamma. And once again, this action descends to one that's proper and co-compact. And of course, the spine is contractible as before. So this is very much a control F and replace of the statement, not necessarily of the proof. Okay, great. So applying the proposition that we used just a moment ago, we straight away get the corollary that the VCD of the untwisted subgroup is bounded above by the dimension of the spine. Sorry, of the untwisted spine. Okay, so it's not so, we don't have a nice closed form like 2n minus 3 to be able to say, oh yeah, here it is. But one can compute the dimension of K gamma sort of just with the graph gamma and with a lot of patience or a computer or both. But in principle, it can be read off from the graph. So that's great. We've got an upper bound. What about a lower bound? The first thing that you might try to do is sort of the same thing that worked for us in the free group case. Let's find large rank free abelian subgroups. So a theorem from 2019, Ben Millard and Karen Vogtmann, says that all sort of nice, like free abelian subgroups that you sort of expect to show up or like naturally generated of the untwisted subgroup have rank bounded above by this quantity rho gamma, which we'll call the principal rank. Okay, and actually better than that, equality is achieved. There is a naturally generated z to the rho gamma sitting as a subgroup inside u of a gamma. I don't want to get into what naturally generated, what I mean here, but just sort of you can sort of write down all of the free abelian subgroups that you might expect to find, and what we're saying is they all have rank at most rho gamma, and one of them actually does. At least one of them actually does have rank rho gamma. Okay, so this gives us a lower bound. We've got rho gamma is less than or equal to the BCD, which is less than or equal to the dimension of the spine. So now what I would love to be able to do is scroll down and say theorem summon saying rho gamma is always equal to the dimension of the spine. Unfortunately, that's not true. So here's the simplest example I'm 99% willing to claim of this breaking down. So here we've got this graph T2, and it's got principal rank rho equal to 5, but the dimension of the spine is 6. Okay, so the VCD is either 5 or 6, but we don't know which. And I'd just like to take a minute to sort of spell out how we feel about each situation. Okay, so if it's 5, then sort of from an algebraic point of view, we're happy, right? We do have a z to the 5 that's naturally generated sitting inside u of a gamma, and sort of somehow this is realizing the VCD in a completely nice algebraic way. However, we're not necessarily all too pleased geometrically, because the spine, which hitherto has been, always the correct dimension, now sort of has an extra dimension floating about, which is a bit surprising. Sort of the other option is that it's 6. The VCD is 6, in which case the spine is exactly what you would want it to be, or there's good evidence that it's exactly what you want it to be, because after all, you couldn't have all of these nice properties to the action on a space of dimension less than 6 if the VCD is equal to 6. Remember that proposition. But us being sort of happy with the spine means that sort of algebraically we're less happy than we were in the free group case, because now there isn't a sort of naturally generated z to the 6 sitting inside u of a gamma that just realizes the VCD in this way. Okay, it's possible that there's some other free abelian subgroup of rank 6, which sort of is unexpectedly generated or something. Or of course it's possible that there just isn't a z to the 6 in there at all, and there is no free abelian subgroup which realizes the VCD. So we've got a little bit of a dichotomy. And in fact, another theorem from the same paper says that, okay, it's the first option. The VCD is 5 in this case, and algebraically we're golden, but we're a bit surprised because the spine has an extra dimension. Okay, so they say that if gamma is something called barbed, this is just some graph theoretic condition, which I don't really want to get into right now because it'll require like 2 more definitions, but it's just something you can read off from the graph. So if it's barbed and this gap between the principal rank and the dimension of the untwisted spine occurs, then you can actually tighten the upper bound by 1. Okay, I'll maybe talk a little bit about the strategy of that proof at the end of the talk. Okay, fine. However, oh, sorry. It so happens that T2 is barbed, so you can apply the theorem in that case. Okay, so let's go to the next suite of examples. So instead of T2, I'm taking other values of 2. So TD, where you've got D of these sort of double leaf things. I hope it's clear which graph I mean. So a computation I did in my master's was to show that the principal rank is 3D minus 1, and the dimension of the spine in this case is 4D minus 2. So now we've got a much sort of bigger gap in general, and in principle a VCD could be sort of anywhere in this range, and all the comments I made before about being algebraically or topologically a little bit squeamish apply. Okay, so the first theorem I'd like to show is that if sort of is a partial resolution to this issue. So if gamma is, okay, unfortunately here's another slightly different condition to barbed called spikiness. It's got a similar vibe, which is why I call it spiky. It's not exactly the same. But so if gamma is spiky, then you can do an equivariant deformation retraction of the spine to some sort of smaller complex k gamma hat. Okay. And okay, this is contentless as it stands. I mean, I could just choose the trivial deformation retraction and say, yeah, I've got a theorem. But the point is that if gamma is also barbed, okay, so to make this work, I have to say, like, it has to be spiky and barbed. If it's also barbed, then the dimension of this new complex is exactly the principal rank. So it's the lower bound. Okay, so this means that in all of these cases that gamma is both spiky and barbed, then we've computed that the VCD is the principal rank. Okay, and sort of this comes with other good news, which is that, okay, first of all, it's realized by this large free abelian subgroup that Millard and Vogtmann found. It's realized as the rank of that 3D minus 1, or that principal rank subgroup. But also we've now got a complex which is also of sort of the correct dimension, if you like. Okay, and I will comment that this you must be both spiky and barbed, and one does not imply the other or anything. Okay, another sort of corollary which I find quite fun is that if you apply this to the TD graphs, this sort of family of examples, then you can. This shows that the gap between the dimension of the untwisted spine and the VCD of the group can be arbitrarily large, right? Because we've just shown that the dimension of the spine, but the VCD is always 3D minus 1, while the dimension of the spine is always 4D minus 2. So there's like linearly growing gap between the two, which is sort of quite surprising if you're coming from it from the free group point of view. It's a bit odd that you can find these many sort of dimensions just floating about in the spine, so to speak. Okay, hopefully at the end I'll get a chance to talk a little bit about the proof. But for now I'm going to slightly change tack and talk about sort of some related work. So I'm going to talk about symmetric automorphisms. So an automorphism is symmetric if it sends each generator to a conjugate of, okay, possibly the inverse of a generator. Okay, it could be sent to a conjugate of itself, but in general, it needn't. And so then you can form the symmetric automorphism group, which I'm denoting with a sigma aught here. And then its image under the quotient aught to out is the symmetric outer automorphism group. And actually, you can show that this is generated by the first three families in that Servacius-Lawrence theorem that I said above. So it's generated by the graph symmetries, the inversions, and the partial conjugations. But so we're throwing out both the twists and the folds. It's not particularly important to remember all of these nouns. It's just a sort of nice class, and in particular, it's a subgroup of the untwisted subgroup. Okay. So for the third time, I'm going to control F and replace. So here's something I'd like to present, which is that if you just, one can build also a symmetric outer space. Okay, so this is a complex upon which the symmetric outer automorphism group acts properly. It's contractible, has a deformation retract to a symmetric spine, which is obviously also contractible, and the action descends to one that's additionally co-compact. Okay, so the proof of this is it's a little bit of a funny story, and I'll get to it just after sort of stating something else that sort of comes with it. So you can also compute the VCD of the symmetric outer automorphism group to be exactly the dimension of this symmetric spine. Okay, so in other words, we're back in the nice land of what happens in free groups. Okay, the spine is exactly the right dimension when you're looking at it from the point of view of VCD. Okay, so the upper bound once again follows just straight away from this theorem and applying the proposition. The lower bound takes a bit more work. You can adapt the Millard-Vogtmann work in the untwisted case and get sort of a symmetric principal rank. And once again show that you've got large free abelian subgroups which realize it. And then sort of the step that didn't work in the untwisted case is to prove that this symmetric principal rank is always equal to the dimension of this symmetric spine. So now we've got an upper bound and a lower bound which coincide, so we're done. And once again, sort of this VCD is realized both algebraically by an actual subgroup, and that sort of is nicely generated, and sort of geometrically as dimension of a space upon which there's a really nice action. Okay, so a comment about this theorem too. Okay, so we've seen the statement 3 times in some sense. So originally I was just basically doing this as like this should work because Don Collins did it in 1989 for free groups, and it was just supposed to be a straight generalization. And I sort of set off with a cowboy hat on saying, okay, well, this is just going to work. And he used Culler-Vogtmann, and I would be able to use the Charney-Stambach-Vogtmann untwisted outer space instead. However, there's a funny sort of roadblock because Culler-Vogtmann's proof is actually stronger than simply the statement that the spine is contractible. And Collins actually used the proof as opposed to the statement. So Culler and Vogtmann showed that for any sort of arbitrary finite set of quantity classes of the free group, you can build some complex KNW. Let me not say what it is, but it's got a deformation retraction from the spine onto it. Okay, so no matter what finite set of quantity classes W you start with, you can always build this thing. And then sort of that's the big move in the proof. And then sort of the last little bit is just pick a clever W naught, such that this Kn W naught is obviously contractible. Okay, and then since Kn is retracting onto something contractible, it must also be contractible. So Collins sort of picked a different, clever for his cases, W1, And then we've got these like deformation retract from something contractible, the spine, onto KNW1, which by the way now also must be contractible by the proof. And then sort of all of his hard work was showing that KNW1 deformation retracts onto his KN sigma, onto his symmetric spine. Okay, so if I want to be able to sort of generalize this second retraction, which is all of Collins's really nice, like clever arguments, then I actually need to be able to produce the thing in the middle, this KNW1. But the problem for me is that Charney, Sandbach, Vogtmann sort of didn't do this overpowered strategy. They just started with the analog of KNW naught, like the kind of the obviously contractible thing, and sort of did the Culler-Vogtmann proof backwards and sort of built up to the full spine rather than retracting down. So sort of this was a necessary step in the way, this next statement. So take any finite set of conjugacy classes of the RAAG, and then there's a deformation retraction from the untwisted spine onto the analog K gamma W. Okay, so now I've basically said now we've got all the jigsaw pieces for how we prove this theorem 2, which is the symmetric outer space one. You pick a W1 like Collins did and sort of generalize his arguments to do a deformation retraction from the appropriate space down to the symmetric spine, and then you show that it's and then this KW1 must be contractible by theorem 4, using the fact that the untwisted spine is contractible. Okay, so there's actually a sort of corollary of the proof, which is that for if I take any finite set W of conjugacy classes and let out sub W of A gamma be the group which permutes the elements of W, preserving the set, then this K gamma W is realizes out W of A gamma as a group which is type VF. So a group is type F if it's got a finite KG1 complex, and then it's type VF if it's virtually type F. So there's a finite index subgroup which has a finite KG1 complex. Okay, so don't worry too much about necessarily what this is, but the point is that this is like another nice finiteness condition on this group out W of A gamma. Okay, so I can stop there. I'm not sure if I've got 25 minutes plus 5 for questions or 30 minutes on the nose, Gemma.
It's kind of a bit of both. So you've got 2 minutes, which you could stop now and have questions, or stop early.
Okay, how about I say I'll stop now, and I have prepared material on the proof of theorem 1, the retraction of the to this K gamma hat. And someone is willing is welcome to ask me if they wish, but obviously they don't have to.
Okay, great. Let's thank Gabriel for a lovely talk. Okay, does anyone have any questions?
Can I ask a question?
Yeah.
Is this corollary like an immediate corollary, or is it like a bunch of work?
It's not immediate, but it's not like it's not too hard.
Okay.
It's sort of that there's already this corollary is that there's an analogous corollary in Culler-Vogtmann for free groups.
Okay, and it's like using Brown's machinery and of the like, or okay.
As in, do you mean this proposition or
This corollary here, like to get type VF, like how do you get it out of like the theorem?
Yeah, so it's these spaces K gamma W. Okay, and so then exactly then you show the the stabilizers are finite under the
Okay, and then you play with that kind of stuff. Okay, thanks.
it's like there's nothing special in the RAAGs case.
Okay.
In this,
any final questions? Okay, let's thank our speaker again.